The history of light before Planck is a fascinating tale of human curiosity and exploration, stretching across centuries of experimentation, observation, and intellectual development. In ancient civilizations, light was not merely a physical phenomenon. It was imbued with mystery and often associated with divine forces. People tried to explain the nature of light through their cultural, religious, and philosophical lenses, often creating elaborate myths and metaphysical theories. One of the earliest known records of human thought about light comes from ancient Egypt and Mesopotamia, where light played an essential role in the mythologies and rituals of the time. In these cultures, the sun was often seen as a god or divine force, a symbol of creation, life, and enlightenment. Ancient Egyptians worshipped the sun god Ra, who represented light, life, and the creation of the world. This reverence for light was also reflected in the architectural design of Egyptian temples and pyramids, where light was carefully manipulated to align with celestial events. In Greece, the nature of light was debated by philosophers such as Pythagoras and Empedocles. Pythagoras, one of the earliest Greek philosophers, proposed that light was a form of emanation or radiation. He believed that objects emitted light in the form of pulsations, which then traveled through the air to the observer's eyes. This idea was consistent with his broader theories about the nature of the universe, which he viewed as being governed by mathematical proportions and harmony. According to Pythagoras, light was not just a physical phenomenon but also a spiritual one, representing the connection between the divine and the material world. Empedocles, another Greek philosopher, also made contributions to the understanding of light. He suggested that vision was the result of a combination of light and the eye's perception. Empedocles proposed that the eye emitted visual rays which, upon contact with an object, allowed the viewer to see it. In this way, vision was not just a passive reception of light, but an active interaction between the eye and the world. This idea laid the groundwork for later theories, though it would eventually be replaced by more accurate scientific explanation. The ancient Greeks also recognized the importance of reflection and refraction. Philosophers such as Euclid and Hero of Alexandria made important contributions to the understanding of light's behavior. Euclid, a mathematician and geometer, was the first to describe the laws of reflection, stating that the angle at which light strikes a surface is equal to the angle at which it is reflected. Hero, a brilliant inventor and engineer, is credited with discovering that light can be refracted as it passes through different mediums, such as from air into water or glass. These early observations about the behavior of light, though rudimentary by modern standards, set the stage for later developments in optics. As the centuries passed, the study of light was increasingly influenced by the rise of more empirical and experimental approaches. In the Middle Ages, Islamic scholars and scientists made significant advancements in the study of optics and light. Figures such as Alhazen ibn al-Haytham, often referred to as the father of optics, revolutionized the understanding of light and vision. Alhazen conducted experiments that demonstrated the role of light in vision and the importance of reflection and refraction. His book of Optics, which was written in the 11th century, laid the foundations for modern optical science. Alhazen argued that light entered the eye and was responsible for vision, challenging earlier ideas that vision was a process of light emanating from the eye. His empirical approach to the study of light and vision was groundbreaking and would influence later thinkers in both the Islamic world and Europe. The Renaissance marked a period of great scientific discovery, and this era saw a renewed interest in the study of light. With the advent of new technologies, such as the telescope and microscope, scientists began to make more detailed observations of the world around them. During this time, the study of optics flourished, and many important discoveries were made regarding the behavior of light. One of the most influential figures during this period was Johannes Kepler, whose work on the nature of vision and the behavior of light in the eye led to the formulation of Kepler's laws of planetary motion. Kepler's insights into the way light interacts with the eye also laid the groundwork for later developments in the study of optics and vision. Another key figure in the Renaissance era was Galileo Galilei, who made groundbreaking contributions to the understanding of light through his development of the telescope. Galileo's observations of the moons of Jupiter and the phases of Venus were made possible by the use of telescopic lenses, which relied on the bending and focusing of light. Galileo's work marked the beginning of modern astronomy, and his use of light to observe distant objects in the universe was a major leap forward in scientific inquiry. Despite these significant contributions, the true nature of light remained shrouded in mystery until the 17th century. During this period, two competing theories of light emerged: the particle theory, championed by Isaac Newton, and the wave theory, which was proposed by Christian Huygens. Both of these theories sought to explain the behavior of light, but neither was able to fully capture its true nature. Newton's corpuscular theory of light, which he developed in the late 17th century, posited that light was composed of tiny particles called corpuscles. According to this theory, light traveled in straight lines and exhibited properties similar to other particles, such as the ability to reflect and refract. Newton's theory was largely based on his work with the prism, through which he demonstrated that white light could be split into its component colors. His work in this area helped establish the idea that light could be treated as a stream of particles. Huygens, on the other hand, argued that light behaved as a wave. He proposed that light was a disturbance that propagated through a medium much like sound waves travel through air. Huygens' wave theory explained phenomena such as diffraction and interference, which could not be easily explained by Newton's corpuscular theory. The debate between the wave and particle theories of light persisted for many years, with both sides offering compelling arguments and evidence. In the 19th century, the wave theory of light gained further support through the work of Thomas Young and Austin Jean Fresnel. Young's famous double-slit experiment in 1801 demonstrated that light could interfere with itself, producing patterns of constructive and destructive interference. This phenomenon could only be explained by the wave theory, and Young's results provided strong evidence in favor of this view. Fresnel further advanced the wave theory by developing mathematical models that explained the behavior of light waves, including their ability to bend around obstacles and pass through narrow openings. By the mid-19th century, the wave theory of light had become the dominant explanation for the behavior of light, but some questions remained unanswered. In particular, scientists were puzzled by the nature of light's transmission through space. How could light travel through the vacuum of space if it was a wave? This question would remain unresolved until the development of James Clerk Maxwell's electromagnetic theory in the 1860s. Maxwell's theory of electromagnetism unified electricity, magnetism, and light into a single framework. He proposed that light was an electromagnetic wave, oscillating electric and magnetic fields that propagated through space. This theory not only explained how light could travel through a vacuum, but it also predicted the existence of other electromagnetic waves, such as radio waves and X-rays. Maxwell's equations were a milestone in the history of physics and provided a comprehensive understanding of light's behavior, laying the groundwork for the developments that would follow in the 20th century. Despite the success of the wave theory, there were still unresolved issues. The most significant of these was the problem of black-body radiation. Classical physics could not explain the observed radiation emitted by hot objects, leading to what was known as the ultraviolet catastrophe. This paradox highlighted the limitations of classical theories of light and set the stage for the next major breakthrough in the history of light, the quantum theory introduced by Max Planck. Planck's work in the late 19th century would forever change our understanding of light. He proposed that energy is quantized, existing in discrete units or quanta. This radical idea solved the problem of black-body radiation and marked the birth of quantum mechanics, a theory that would eventually revolutionize our understanding of the microscopic world. In conclusion, the story of light before Planck is a rich tapestry of ideas, theories, and discoveries that spans thousands of years. From the mystical views of ancient civilizations to the empirical investigations of the Renaissance and the wave particle debate, the history of light is a testament to humanity's insatiable curiosity and drive for knowledge. It was only with the advent of quantum theory that the true nature of light was revealed, forever altering our perception of the universe. As the 19th century drew to a close, scientific inquiry into the nature of light had advanced significantly, yet many fundamental questions remained unresolved. Despite the development of theories that could explain various aspects of light, there was still a major gap in understanding its behavior at the atomic and subatomic levels. The inability of classical physics to explain phenomena like black-body radiation and the ultraviolet catastrophe would ultimately pave the way for the revolutionary ideas that would reshape the study of light and lead to the emergence of quantum mechanics. The ultraviolet catastrophe, which emerged from the study of black-body radiation, became one of the most pressing problems in physics. Classical physics, relying on the laws of electromagnetism and thermodynamics, predicted that a perfect black body, an idealized object that absorbs all radiation incident upon it, should emit infinite amounts of radiation as the temperature increased, particularly at shorter wavelengths, like ultraviolet light. This was clearly not observed in experiments where the radiation emitted by hot objects peaked at a certain wavelength before declining. Classical theories, including those of Rayleigh and Jeans, predicted a sharp increase in radiation intensity at shorter wavelengths, but this was not seen experimentally. This discrepancy, known as the ultraviolet catastrophe, challenged the prevailing understanding of light. In 1900, the solution to this problem came from an unexpected source, Max Planck. Planck, a German physicist, was attempting to resolve the issues surrounding black-body radiation. He introduced the idea that energy could only be emitted or absorbed in discrete quantities, or quanta, rather than assuming energy could be transferred continuously as classical theories had done. Planck proposed that energy could only exist in multiples of a fundamental unit, which he called the quantum. This concept of quantization marked the beginning of a paradigm shift in physics. Planck's introduction of the quantum hypothesis was an attempt to explain the observed distribution of radiation intensity in a way that aligned with experimental data, and it worked. The new formula that Planck derived fit the observed radiation curve perfectly, solving the ultraviolet catastrophe. However, Planck's idea of quantization was a mere mathematical trick to fit experimental data. He did not initially believe that it signified a fundamental shift in the way the universe operated. It wasn't until later that his ideas would be fully embraced and expanded upon by other scientists, leading to the formation of quantum theory. Nonetheless, Planck's work laid the foundations for a new way of thinking about energy, light, and matter, and it was this breakthrough that would later influence Albert Einstein, Niels Bohr, and others. Max Planck's work was instrumental in the evolution of light theory, but it wasn't until Albert Einstein's work in the early 20th century that the wave-particle duality of light began to gain widespread acceptance. Einstein's 1905 paper on the photoelectric effect presented a revolutionary interpretation of light. While the wave theory had successfully explained the interference and diffraction of light, Einstein suggested that light could also behave as particles, or photons. In his experiment, he demonstrated that when light of a certain frequency strikes a metal surface, it ejects electrons from the surface, an effect that could only be explained if light were quantized into discrete packets of energy. This was groundbreaking, as it contradicted the long-standing wave theory, which could not explain this phenomenon. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and his concept of light as both a wave and a particle, a theory known as wave-particle duality, became one of the cornerstones of quantum mechanics. This duality, where light could exhibit both wave-like and particle-like properties depending on the circumstance, fundamentally challenged the classical understanding of light as purely one or the other. It was a concept that defied common sense, but was supported by a growing body of experimental evidence. Following Einstein, Niels Bohr further expanded on Planck's idea. With his work on the hydrogen atom, Bohr introduced the concept of quantized energy levels in atoms, which explained the discrete lines seen in atomic spectra. He suggested that electrons could only occupy certain allowed orbits around the nucleus and that energy could only be absorbed or emitted when an electron moved from one orbit to another. This concept of quantization in atomic systems further validated Planck's hypothesis of quantum energy, and it laid the groundwork for the development of modern quantum theory. As the 20th century progressed, the wave-particle duality of light and the concept of quantized energy would continue to evolve. The development of quantum mechanics, spearheaded by scientists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, redefined our understanding of the universe. Schrödinger's wave equation, Heisenberg's uncertainty principle, and Dirac's equation for the relativistic electron all contribute to a new and startlingly accurate framework for understanding light, matter, and the fundamental forces of nature. In addition to these theoretical developments, experimental breakthroughs also played a crucial role in the validation of quantum mechanics. The discovery of the electron in 1897 by J.J. Thomson, the invention of the electron microscope, and advancement in spectroscopy all provided the empirical data that supported the ideas put forth by Planck, Einstein, and their contemporaries. The observation of atomic and subatomic phenomena that could not be explained by classical physics provided a compelling argument for the new quantum theory. The quantum revolution fundamentally transformed not only our understanding of light, but also our understanding of the nature of reality itself. No longer could light be neatly categorized as either a wave or a particle. It was both, depending on how it was observed. This realization had profound implications for the way we think about the universe, as it suggested that reality at the quantum level operates in ways that defy our classical intuitions. Max Planck's contributions to the understanding of light were undeniably crucial, but his work was just the beginning of a larger intellectual revolution. The development of quantum mechanics in the early 20th century shattered the classical worldview and set the stage for the modern understanding of light as a fundamental, dual-natured phenomenon. Planck's work on black-body radiation, though initially a mathematical fix, led to a series of breakthroughs that would transform physics and lead to the creation of technologies that have shaped the modern world, such as lasers, semiconductors, and quantum computers. The nature of light, before Planck, was defined by a long history of philosophical and empirical exploration, filled with ideas that spanned from mystical explanations to the earliest seeds of scientific reasoning. Light was regarded as a force of the divine, an emanation, or a simple stream of particles, and as new experimental techniques emerged, the study of light transitioned into a more rigorous scientific endeavor. The theories of Huygens, Newton, Young, and Maxwell shaped our understanding, but it was Max Planck's breakthrough that set the stage for the quantum revolution. Through Planck's quantum hypothesis, the notion of energy being quantized emerged, and this led directly to the quantum mechanics that would forever alter our understanding of light and the physical world. In conclusion, the story of light before Planck is a narrative of intellectual evolution from ancient philosophical musings to the empirical science that eventually led to the birth of quantum mechanics. It's a story of how humanity grappled with the most fundamental questions about the universe, and how, through perseverance and insight, we began to unlock the mysteries of nature. Planck's contributions, alongside the works of Einstein, Bohr, and others, reshaped our understanding of light, paved the way for the technological and theoretical advancements that continue to influence modern science today. The nature of light, once an enigma, has since been understood in a way that continues to push the boundaries of human knowledge, providing answers to questions that were once thought to be beyond our reach. The concept of light has undergone a remarkable evolution in human thought, transitioning from mystical and philosophical interpretations to empirical investigations and scientific theories. In this narrative, the second keynote focuses on the wave theory of light, which is pivotal in understanding the behavior of light in the context of early modern science. The development of the wave theory marked a significant shift in how scientists conceptualized light, transitioning from the particle-based ideas of earlier philosophers to the wave-based explanations that would dominate much of the 19th century. The wave theory of light, as we understand it today, is rooted in the work of Christian Huygens, a Dutch physicist and mathematician who lived in the 17th century. Huygens' theory of light, first proposed in 1678, was one of the key milestones in the scientific understanding of light. He suggested that light could be thought of as a wave propagating through a medium, which he called the ether. This idea was a significant departure from the particle-based theories of light, such as those proposed by Isaac Newton. Huygens' theory was largely inspired by the observed phenomenon of reflection and refraction of light. He posited that light waves spread out from a point source in all directions, much like the ripples created when a stone is thrown into water. According to his theory, each point on a wavefront could be considered as a new source of waves, propagating outward. This was the foundation of what would later become known as Huygens' principle, which provided a clear explanation for the way light waves travel and interact with various surfaces. The wave theory of light initially faced strong opposition from supporters of Newton's corpuscular theory of light, which held that light was composed of small particles or corpuscles. Newton had established this theory in the 17th century, and it was widely accepted at the time. He argued that light behaved like a stream of particles, explaining phenomena like reflection and refraction. However, when Huygens proposed the wave theory, he opened up new ways of thinking about light's behavior, particularly its ability to diffract and interfere. One of the central challenges for Huygens and his wave theory was to explain the phenomenon of light interference. Interference occurs when two light waves meet and combine, either amplifying or canceling each other out. This was a puzzling phenomenon that Newton's particle theory could not easily account for. Huygens, on the other hand, was able to explain interference through the interaction of light waves, which could add together constructive interference or cancel out destructive interference depending on their relative phase. In the early 19th century, Thomas Young's famous double-slit experiment further validated the wave theory of light. In 1801, Young demonstrated that light passing through two narrow slits created an interference pattern on a screen behind the slits. This pattern, consisting of alternating light and dark bands, could only be explained if light was behaving as a wave. When two slits were open, the waves emerging from each slit interacted with one another, leading to the constructive and destructive interference that produced the observed pattern. Young's experiment was a crucial piece of evidence for the wave theory, as it could not be explained by Newton's particle-based theory. The wave theory of light continued to gain acceptance as more experiments supported it. Augustin-Jean Fresnel, a French engineer and physicist, was instrumental in developing the mathematical framework of the wave theory in the 1810s and 1820s. Fresnel's work on the diffraction and interference of light led to the development of equations that described how light waves behave when they pass through apertures or encounter obstacles. His calculations showed that light could indeed be described as a wave phenomenon, and they were experimentally verified by subsequent experiments. One of the most important consequences of the wave theory of light was the prediction of the phenomena of diffraction and polarization. Diffraction occurs when light waves encounter an obstacle or aperture and bend around it. This bending of light could be observed when light passed through narrow slits, as demonstrated by Young's experiment. Polarization, on the other hand, refers to the alignment of the vibrations of light waves in a specific direction. Light waves can vibrate in various directions, but when light passes through certain materials, such as polarizing filters, only waves vibrating in a specific direction are allowed to pass through. This phenomenon was predicted by the wave theory and later confirmed experimentally by scientists such as Etienne Louis Malus in the early 19th century. Despite the overwhelming success of the wave theory in explaining many aspects of light, there were still unresolved issues. One of the most significant challenges was the question of how light could travel through the vacuum of space. In the wave theory, the medium through which waves travel is crucial. In the case of sound waves, for example, the medium is air, while water waves travel through the ocean. But if light is a wave, what medium does it travel through, especially in the vacuum of space? This problem led to the concept of ether, a hypothetical medium that was thought to fill all of space and provide a medium for light waves to propagate through. The ether theory was widely accepted in the 19th century, and many experiments were conducted to detect its presence. However, by the end of the 19th century, experiments such as the Michelson-Morley experiment failed to detect any sign of the ether. This raised serious doubts about the existence of such a medium and paved the way for the development of new theories in the early 20th century. The culmination of the wave theory of light and the search for the nature of light was the electromagnetic theory developed by James Clerk Maxwell in the mid-19th century. Maxwell's equations, formulated between 1861 and 1865, unified the concepts of electricity, magnetism, and light into a single framework. Maxwell showed that light is an electromagnetic wave composed of oscillating electric and magnetic fields that propagate through space at a constant speed. This theory provided a complete explanation for the behavior of light and successfully answered the question of how light could travel through the vacuum of space. Maxwell's theory of light revolutionized the field of physics and laid the foundation for much of modern electromagnetism. It also explained phenomena such as the reflection, refraction, and polarization of light in a comprehensive manner, and it provided a unified understanding of the nature of light. However, while Maxwell's equations were incredibly successful in explaining many aspects of light, they did not resolve all the issues that had emerged in the 19th century. The most pressing of these was the behavior of light at the atomic and subatomic levels, which classical physics could not adequately explain. The wave theory of light, which had triumphed in the 19th century, was ultimately challenged by the discovery of quantum mechanics in the early 20th century. The development of quantum theory, initiated by Max Planck and further expanded by Albert Einstein, Niels Bohr, and others, revealed that light exhibits both wave-like and particle-like properties. This wave-particle duality was one of the key insights of quantum theory, fundamentally changed our understanding of light and the physical world. Conclusion: the wave theory of light represented a major step forward in our understanding of the nature of light. From Huygens' early proposal to Maxwell's unification of electromagnetism, the wave theory provided explanations for many phenomena that could not be accounted for by earlier particle theories. The discovery of diffraction, interference, and polarization helped to solidify the wave theory as the dominant explanation for the behavior of light in the 19th century. However, the advent of quantum mechanics in the 20th century ultimately revealed that light cannot be fully described as either a wave or a particle, but rather exhibits characteristics of both, depending on the context. The development of the wave theory, followed by the insights of quantum mechanics, has shaped our modern understanding of light and continues to influence the fields of physics, optics, and technology. The development of the wave theory of light is a crucial chapter in the history of physics, and it represents a monumental shift in our understanding of the natural world. By the time of the 19th century, scientists had begun to move beyond the particle-based models of light proposed by Newton and others, and the wave theory offered new explanations for the phenomena observed in light. As the wave theory evolved, it addressed long-standing puzzles about light's behavior and paved way for groundbreaking discoveries that would ultimately lead to the advent of quantum theory. Before Maxwell, the wave theory had successfully explained some aspects of light, but the theory still faced challenges that required further exploration. The idea of light as a wave propagated through a medium called ether remained dominant throughout the 19th century, despite mounting questions about its existence. Ether was imagined to be an invisible substance filling all of space, allowing waves of light to propagate through the vacuum. However, as the 19th century drew to a close, the idea of ether became increasingly untenable, particularly after the famous Michelson-Morley experiment in 1887. Which sought to detect the movement of the Earth through the ether. The failure to detect any sign of the ether led scientists to question the very existence of this medium, and a new understanding of the nature of light was needed. In the meantime, the wave theory of light continued to evolve and gain acceptance. Thomas Young's double-slit experiment 1801 had been pivotal in solidifying the wave nature of light. The experiment demonstrated that when light passes through two closely spaced slits, it produces an interference pattern, which can only be explained by the wave nature of light. Young's findings challenged Newton's corpuscular theory of light, which had been dominant at the time and could not account for the interference patterns observed in the double-slit experiment. Later in the 19th century, Augustin-Jean Fresnel, a French physicist, expanded on Huygens' principle and developed a detailed mathematical model that further validated the wave theory of light. Fresnel introduced the concept of diffraction, which refers to the bending of light waves around obstacles and the spreading of waves when they pass through narrow openings. His work on diffraction was groundbreaking because it showed that light did not travel in straight lines as particles would. Instead, light bent and spread out in patterns that could be mathematically predicted by the principles of wave behavior. Fresnel's equations, derived in the 1820s, were instrumental in explaining phenomena like diffraction and interference, providing compelling evidence in favor of the wave theory of light. While the wave theory was becoming more widely accepted, some of the most significant breakthroughs in understanding light came from James Clerk Maxwell, a Scottish physicist whose equations of electromagnetism unified electric fields, magnetic fields, and light. In the 1860s, Maxwell developed a set of 4 equations, known as Maxwell's equations, which demonstrated that light is an electromagnetic wave, a disturbance in the electric and magnetic fields that propagates through space. Maxwell's unification of electricity, magnetism, and light was a crucial moment in the history of physics, as it provided a theoretical framework for understanding not just light, but a host of other phenomena in the natural world. Maxwell's equations also introduced the concept of the speed of light as a constant, a revolutionary idea at the time. According to Maxwell's theory, the speed of light in a vacuum is determined by the properties of the electric and magnetic fields, and is the same for all observers, regardless of their motion. This insight had profound implications for the development of the theory of special relativity, formulated by Albert Einstein in the early 20th century. However, despite the successes of the wave theory, certain phenomena could not be explained by Maxwell's equations or the wave theory of light alone. One of the most significant of these was the behavior of light at very small scales. At the atomic and subatomic levels, light did not always behave as a continuous wave. Instead, it exhibited particle-like properties, a phenomenon that was demonstrated in the photoelectric effect, where light striking a metal surface causes electrons to be emitted. The wave theory could not explain this effect, which ultimately led to the development of the quantum theory of light. The photoelectric effect was discovered by Heinrich Hertz in 1887, and it was later explained by Albert Einstein in 1905. In this experiment, Hertz found that ultraviolet light striking a metal surface caused sparks to jump between 2 metal electrodes. However, he also noticed that this effect did not occur when the light was dimmed below a certain threshold frequency, even if the intensity of the light was increased. According to the wave theory, light should have been able to eject electrons from the metal at any intensity, as long as the frequency of the light was high enough. However, this was not observed, and the classical wave theory could not account for this behavior. Einstein proposed a revolutionary solution to this problem by suggesting that light is composed of discrete packets of energy, which he called quanta, later called photons. According to Einstein, when light of a certain frequency strikes a metal surface, each photon transfers its energy to an electron, ejecting it from the surface. The photoelectric effect could thus be explained by treating light as discrete particles, rather than as a continuous wave. This marked a major turning point in the study of light, as it challenged the long-standing wave theory and opened the door to the concept of wave-particle duality, the idea that light can exhibit both wave-like and particle-like properties. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and his explanation of the phenomenon laid the foundation for the development of quantum mechanics. The wave-particle duality of light, as demonstrated by the photoelectric effect, was one of the central ideas that would shape the emerging field of quantum mechanics in the 20th century. The wave theory of light, which had dominated scientific thought for much of the 19th century, began to be integrated with new ideas from quantum theory. The discovery that light can behave both as a wave and as a particle ultimately led to the development of quantum mechanics, a revolutionary framework for understanding the behavior of particles and waves at the atomic and subatomic levels. Quantum mechanics, developed by scientists such as Max Planck, Niels Bohr, and Werner Heisenberg, introduced a new way of thinking about the nature of light and matter. According to quantum theory, light and other forms of electromagnetic radiation are quantized and behave as both particles, photons, and waves. Wave-like properties of light, which had been described by Huygens, Young, and Maxwell, were retained, but they were now understood to coexist with the particle-like properties of light, as shown in Einstein's work on the photoelectric effect. The wave theory of light had an extraordinary impact on the field of optics and on our understanding of the natural world. It provided a unified framework for explaining a wide range of phenomena, from the behavior of light in everyday life to the interactions of light at the atomic level. It also laid the groundwork for the development of other areas of physics, such as electromagnetism and quantum mechanics, which would go on to revolutionize our understanding of the universe. In conclusion, the wave theory of light was a critical development in the history of physics that challenged earlier particle-based theories of light and provided the foundation for future discoveries in electromagnetism and quantum mechanics. From the early work of Huygens and Young to the contributions of Maxwell and Einstein, the wave theory offered new explanations for a variety of phenomena, and it ultimately led to the understanding that light behaves both as a wave and a particle. This understanding, which emerged in the 20th century, remains one of the cornerstones of modern physics and continues to shape our understanding of light, matter, and the fundamental forces of nature. The journey into the nature of light before the advent of quantum mechanics is a remarkable tale, woven through the fabric of history, spanning ancient civilizations and culminating in the revolutionary discoveries of the 19th and early 20th centuries. The third keynote in this evolution focuses on the key scientific events and discoveries leading to the eventual synthesis of the particle and wave theories of light. This keynote explores how the attempts to understand light evolved through centuries of observation, experimentation, and the gradual refinement of theories that ultimately culminated in the birth of modern physics. The history of light began long before the scientific method was developed. In the ancient world, light was often associated with the divine and the supernatural. For example, the ancient Greeks speculated that light could be understood as a kind of emanation or radiation. Philosophers like Pythagoras and Empedocles believed that light was an active force that could move from objects and enter the eye, allowing vision. These early notions, while rudimentary, set the stage for centuries of inquiry into the nature of light. Even the very word photon, which we use today to describe light particles, finds its roots in these ancient ideas. However, as science began to take shape in the Renaissance, the study of light became more systematic. With the advent of the microscope and telescope in the 16th and 17th centuries, scientists such as Johannes Kepler and Galileo Galilei began to make detailed observations about light's behavior. Kepler, for example, worked on understanding how light passed through the eye, and Galileo used his telescope to observe the moons of Jupiter, providing insights into the way light could be manipulated through lenses. The tools of observation in this period allowed a more empirical and scientific approach to the study of light. This shift in methodology marked a crucial turning point. By the late 17th century, Sir Isaac Newton had become a leading figure in the study of light. Newton's contributions to understanding light were monumental. He proposed that light was composed of particles, which he called corpuscles. His corpuscular theory of light dominated scientific thinking for nearly a century, and Newton's work with prisms and the colors of light had lasting effects on the way scientists viewed the nature of light. Newton demonstrated that white light could be separated into its component color by passing it through a prism, leading him to argue that color itself was an inherent property of light. This work on optics laid the groundwork for later developments in the field. Despite the success of Newton's corpuscular theory, questions about light's behavior began to emerge in the 19th century that Newton's theory could not explain. The nature of light interference, diffraction, and polarization raised doubts about the accuracy of the particle model. The most significant challenge came from the phenomenon of interference, which was demonstrated experimentally by Thomas Young in 1801. Young's famous double-slit experiment showed that light passing through two slits produced an interference pattern, a series of alternating light and dark bands on a screen. This could only be explained by the wave theory, which proposed that light, sound waves or water waves, would interfere with itself, creating these patterns. Young's experiment was a critical moment in the history of light. It challenged the previously accepted particle theory, which could not explain interference, and provided strong evidence that light behaves like a wave. This idea of light as a wave was further developed by Augustin-Jean Fresnel, a French engineer and physicist. Fresnel worked on the mathematics of diffraction and polarization, showing how light waves could bend around obstacles and pass through small openings. His work was instrumental in advancing the wave theory of light and establishing it as the dominant model for understanding light in the 19th century. Fresnel's theories were so powerful that they eventually led to a new understanding of how light behaves. This was particularly important in understanding phenomena such as diffraction, where light bends around obstacles, and interference, where waves from two light sources meet and either cancel each other out or reinforce each other. In the context of optical devices like lenses and mirrors, the wave theory provided a more accurate framework for predicting how light would behave under various conditions. For example, Fresnel's equations allowed scientists to understand the behavior of light when it passed through different materials or interacted with surfaces in complex ways. By the mid-1800s, the wave theory of light was firmly established, and scientists like James Clerk Maxwell had begun to develop a more comprehensive understanding of light's nature. Maxwell's equations, formulated in the 1860s, revolutionized our understanding of light. Maxwell showed that light is an electromagnetic wave, meaning it is composed of oscillating electric and magnetic fields that propagate through space. This was a breakthrough in understanding light because it united the concepts of electricity and magnetism, which had previously been studied as separate phenomena. Maxwell's equations also predicted that light travels at a constant speed, and his theory suggested that light, like other electromagnetic waves, could travel through a vacuum without the need for a medium like the ether. Maxwell's work was groundbreaking because it not only unified the forces of electricity and magnetism but also showed that light was just one form of electromagnetic radiation. This understanding opened the door for a wide range of new discoveries, including radio waves, X-rays, and gamma rays. Maxwell's equations also implied that light could travel through space without the need for any material medium, rendering the concept of ether obsolete. Despite the success of Maxwell's theory in explaining the wave nature of light, the theory still had its limitations. One of the biggest puzzles was black-body radiation. According to classical physics, the energy radiated by a perfect black body, an object that absorbs all incoming radiation, should increase without bound as the temperature rises, especially at shorter wavelengths, like ultraviolet light. This discrepancy between theory and experiment became known as the ultraviolet catastrophe. Classical physics could not explain the observed radiation curves of hot objects, leading to a major crisis in physics. In 1900, the solution to the ultraviolet catastrophe came from Max Planck. Planck's work laid the foundation for what would later become quantum mechanics. To solve the problem of black-body radiation, Planck proposed that energy could only be emitted or absorbed in discrete units, which he called quanta. This idea of quantized energy was radical, as it suggested that energy was not continuous, as classical physics had assumed, but rather came in discrete packets. Planck's quantum hypothesis successfully explained the observed radiation curve, and it marked the beginning of a new era in physics. The introduction of the quantum hypothesis by Planck in 1900 set the stage for the eventual development of quantum theory. However, Planck's idea of quantized energy was initially just a mathematical trick to fit experimental data. It wasn't until Albert Einstein's work on the photoelectric effect in 1905 that the true significance of Planck's quantum hypothesis became clear. Einstein proposed that light was not just a wave as had been previously thought, but also behaved like a particle. His work on the photoelectric effect, where light struck a metal surface and ejected electrons, could only be explained if light were composed of discrete packets of energy, photons. Einstein's theory of light as both a wave and a particle, known as wave-particle duality, was a revolutionary breakthrough. It showed that light could exhibit both wave-like and particle-like properties depending on how it was observed. This realization would eventually lead to the development of quantum mechanics, which would fundamentally change our understanding of the behavior of light and matter at the atomic and subatomic levels. The story of light before Planck and Einstein is one of gradual progress from early mystical and philosophical interpretations to rigorous empirical science. From the ancient Greeks to the 19th century pioneers, each scientist built on the work of those who came before them, refining the theories of light and solving the puzzles that emerged along the way. It is a testament to human ingenuity and curiosity as scientists grappled with one of the most fundamental aspects of the natural world. In conclusion, the evolution of light theories from ancient times through the 19th century laid the groundwork for the groundbreaking developments of the 20th century. The wave theory, developed by figures like Huygens, Young, and Maxwell, provided a deep understanding of light's behavior and paved the way for the later discoveries that would transform our understanding of the universe. Planck's and Einstein's contributions to quantum theory marked the beginning of a new era in physics, one that would continue to expand our knowledge and push the boundaries of what we know about the nature of light. The quest for understanding the nature of light is a story that spans centuries, from ancient civilizations to the early 20th century. As human knowledge and technology evolved, so too did the theories and ideas about the fundamental properties of light. The early 19th century represented a critical juncture in this journey, as the wave theory of light began to gain dominance over the particle theory. This shift in understanding was driven by a series of groundbreaking experiments and mathematical formulations that reshaped the scientific community's perception of light. In this phase of exploration, a pivotal step was the unification of light with electromagnetism, a step that would eventually lead to the quantum revolution. This chapter in the history of light is defined by the transition from classical theories, such as Newton's corpuscular theory, to the more comprehensive and unifying wave theory of light, which ultimately paved the way for the discoveries of quantum physics. The first key moment in this transformation came with the works of Thomas Young in 1801, who performed his famous double-slit experiment. Before this experiment, light had been widely thought to behave like a particle, in accordance with Newton's corpuscular theory. Newton's particle-based theory of light, established in the late 17th century, posited that light was composed of tiny particles, or corpuscles, that traveled in straight lines and interacted with materials based on their size and motion. Newton's ideas explained phenomena like reflection and refraction but failed to account for certain behaviors of light, such as interference. Young's double-slit experiment provided the first clear evidence of light's wave nature. In his experiment, Young passed light through two closely spaced slits and observed that it created a pattern of alternating light and dark bands on a screen. This interference pattern, which occurs when two waves interact with one another, could only be explained if light were a wave, as particles do not interfere with each other in this way. Young's discovery was groundbreaking, as it demonstrated that light could exhibit characteristics of waves, something that was previously not considered. This discovery challenged Newton's particle theory, setting the stage for further exploration of light as a wave. In addition to Young, another important figure in the wave theory of light was Augustin-Jean Fresnel, a French engineer and physicist. Fresnel expanded on Young's findings by developing mathematical models to explain the diffraction of light, the bending of light waves as they pass around obstacles or through small openings. Fresnel's work demonstrated that light did not travel in straight lines as particles would, but instead exhibited wave-like properties such as interference and diffraction. His theories not only explained the behavior of light through slits and around obstacles, but also helped to unify the understanding of how light interacted with materials and surfaces. Fresnel's work provided the scientific foundation for the development of modern optics, and was instrumental in solidifying the wave theory of light. The significance of Fresnel's work was profound, because it provided a comprehensive mathematical framework for understanding light as a wave. It explained why light could be diffracted and why certain patterns occurred when light passed through slits. Fresnel's equations, derived in the 1820s, became central to the study of optics and laid the groundwork for many optical devices, including microscopes, telescopes, and cameras. By offering a mathematical understanding of diffraction, Fresnel's work allowed for predictions about the behavior of light that could be tested experimentally, further solidifying the wave theory. In the 19th century, the wave theory of light became the dominant explanation for its behavior. However, the question remained of how light, as a wave, could travel through the vacuum of space. This problem arose because, in classical physics, waves were understood to require a medium through which to propagate, such as air for sound waves or water for ocean waves. Scientists needed to explain how light could travel through the seemingly empty space. This led to the concept of the ether, a hypothetical medium that was thought to permeate the universe and serve as the medium for light waves. The ether theory, while never directly observed, became widely accepted in the scientific community during the 19th century. According to this theory, the ether was an invisible substance that filled all of space, providing the necessary medium for light waves to propagate. However, as the 19th century progressed, Experiments aimed at detecting the ether began to fail. The most famous of these was the Michelson-Morley experiment of 1887, which attempted to detect the motion of the Earth through the ether. The experiment failed to find any evidence of the ether, suggesting that it did not exist. This result was puzzling because, according to the wave theory of light, the ether was supposed to be the medium through which light traveled. The failure to detect the ether led to a major crisis in physics, as scientists were forced to reconsider the nature of light and the assumptions upon which the wave theory was built. The failure of the ether theory was a critical moment in the history of light and paved the way for the eventual development of special relativity and quantum mechanics. As scientists grappled with the implications of the Michelson-Morley experiment, a new understanding of light began to emerge, one that did not rely on the existence of the ether. This new perspective was provided by James Clerk Maxwell, a Scottish physicist whose groundbreaking work unified the theories of electricity, magnetism, and light. In the mid-19th century, Maxwell formulated his famous equation of electromagnetism, which showed that light is an electromagnetic wave. Maxwell's theory was revolutionary because it not only explained light's behavior as a wave but also demonstrated that light, along with other electromagnetic waves, could propagate through the vacuum of space. Maxwell's equations showed that light was an oscillating electric and magnetic field, and these fields could travel through space at a constant speed. This breakthrough solved the problem of how light could travel through a vacuum, as it no longer needed a medium like the ether. Maxwell's equations not only unified the concepts of electricity and magnetism, but also provided a comprehensive theory of light that accounted for a wide range of phenomena, including reflection, refraction, diffraction, and interference. Maxwell's unification of electricity, magnetism, and light into a single framework was one of the most significant achievements in the history of physics. His equations provided a mathematical description of electromagnetic waves, which included visible light as a subset of the broader electromagnetic spectrum. The implications of Maxwell's theory were far-reaching, as it not only unified several aspects of physics but also predicted the existence of other electromagnetic waves, such as radio waves, X-rays, and gamma rays. Maxwell's equations became the foundation for much of modern physics and helped to propel the study of light into the 20th century. While Maxwell's theory of electromagnetism was a monumental achievement, it did not completely resolve all the questions surrounding the nature of light. One of the most pressing problems was the phenomenon of black body radiation. Classical physics predicted that the radiation emitted by a perfect black body, an object that absorbed all radiation, would increase without limit as the temperature rose, especially at shorter wavelengths. However, experimental data showed that the radiation emitted by hot objects peaked at a certain wavelength and then decreased at higher frequencies. This discrepancy became known as the ultraviolet catastrophe, and it posed a major challenge to classical physics. The resolution of the ultraviolet catastrophe came from Max Planck, who in 19 proposed a solution that involved the quantization of energy. Planck suggested that energy could only be emitted or absorbed in discrete units, which he called quanta. This concept of quantized energy was revolutionary and laid the foundation for what would later become quantum mechanics. Planck's work solved the problem of blackbody radiation and demonstrated that the energy of electromagnetic waves was not continuous, but rather came in discrete packets. This was a pivotal moment in the history of light, as it marked the beginning of a new era in physics, where the behavior of light would be understood not just as a wave, but also as a particle. The next major step in the story of light was Albert Einstein's work on the photoelectric effect in 1905, which extended Planck's ideas into a new understanding of the particle nature of light. Einstein proposed that light could behave as both a wave and a particle, a concept known as wave-particle duality. This was a radical departure from the classical view of light and laid the groundwork for the development of quantum theory. Einstein's work on the photoelectric effect, for which he was awarded the Nobel Prize in 1921, showed that light could be treated as discrete packets of energy, photons, which behave like particles in certain circumstances. In conclusion, the story of light before Planck is a tale of evolving theories, each building upon the discoveries of those who came before. From the early wave theories of Huygens and Young to Maxwell's unification of electromagnetism, the understanding of light gradually expanded to incorporate both its wave-like and particle-like properties. This understanding reached its apex with the birth of quantum mechanics, a theory that redefined the nature of light and matter. The shift from classical physics to quantum physics represented a monumental leap in our understanding of the universe, and the study of light remains at the forefront of scientific inquiry today. The journey of light's understanding has been long and intricate, filled with many groundbreaking discoveries. The fourth keynote in this journey focuses on the significant shift in our understanding of light's nature, particularly the pivotal development of electromagnetic theory in the 19th century. Light, once a mystery, gradually became understood as a wave phenomenon, and the theories that emerged during this period were essential in shaping the modern understanding of light. At the heart of this shift is the work of James Clerk Maxwell, whose groundbreaking contributions unified electricity, magnetism, and light into one coherent theory. Prior to Maxwell's work, scientists treated electricity and magnetism as separate phenomena with little understanding of how they were connected. Maxwell's theory, developed in the mid-1800s, demonstrated that light is a form of electromagnetic radiation, an oscillating electric and magnetic field that propagates through space. This discovery was revolutionary because it not only explained light's behavior but also predicted the existence of other forms of electromagnetic radiation, such as radio waves and X-rays. Maxwell's equations, formulated between 1861 and 1865, show that electromagnetic waves travel at a constant speed, which is the speed of light. This relationship between light and electromagnetic waves was a monumental step in the history of physics, as it unified several previously isolated fields. Maxwell's theory also explained how light can travel through a vacuum, which solved the problem that had puzzled scientists for centuries. How can light travel through empty space if it is a wave? Maxwell's equations demonstrated that the electric and magnetic fields could propagate through space, allowing light to travel without requiring a medium, like the hypothetical ether that had been proposed earlier. This unification was crucial because it provided a mathematical framework that not only explained light's behavior but also extended the understanding of other forms of electromagnetic waves. Maxwell's work paved the way for the development of many modern technologies, from radio to television to wireless communication. It also influenced later developments in physics, especially the theory of special relativity proposed by Albert Einstein in 1905. Einstein's theory built on Maxwell's ideas by incorporating the constant speed of light and suggesting that the laws of physics, including those governing light, are the same for all observers, regardless of their motion. While Maxwell's electromagnetic theory succeeded in explaining the wave-like nature of light, there were still puzzles to solve. The wave theory, while successful in many areas, was unable to explain certain phenomena that came to light at the end of the 19th century. One of the most pressing of these was the phenomenon of black body radiation, which led to what became known as the ultraviolet catastrophe. Classical physics predicted that a black body, an idealized object that absorbs all radiation, would emit infinite amounts of energy at short wavelengths, particularly in the ultraviolet range. However, experimental observations showed that this was not the case. The energy emitted by black bodies increased with temperature, but did not follow the predicted pattern at shorter wavelengths. This paradox pointed to the limitations of classical physics and demanded a new approach to understanding light at microscopic levels. The resolution of this problem came from Max Planck in 1900, who introduced the idea of quantized energy levels. Planck suggested that energy is not continuous, as classical theories assumed, but rather exists in discrete units called quanta. This insight was revolutionary and laid the foundation for the development of quantum mechanics. Planck's work solved the blackbody radiation problem by introducing the idea that energy was exchanged in specific amounts, providing the necessary explanation for the observed radiation curves. Einstein's work on the photoelectric effect, following Planck's introduction of quantized energy, further solidified the understanding that light could exhibit both wave-like and particle-like properties. Einstein showed that light could be thought of as particles, photons, which helped explain phenomena that the wave theory could not. This dual nature of light, both a wave and a particle, became one of the central pillars of quantum mechanics, which fundamentally transformed our understanding of the universe. Together, The work of Maxwell, Planck, and Einstein reshaped the study of light, revealing its complex, dual nature and setting the stage for future advancements in physics. The story of light's understanding takes a profound turn with the fifth keynote, which delves into the development of quantum mechanics, an area of physics that fundamentally altered our conception of light. The pivotal breakthrough came in the early 20th century when Max Planck introduced the concept of quantization, which began to resolve the long-standing issue of blackbody radiation. The classical theories could not explain why the radiation emitted by a perfect black body, an idealized object that absorbs all incoming radiation, did not match the prediction. Instead of the infinite increase in radiation predicted at higher frequencies, experimental results showed that the radiation intensity decreased. This paradox was known as the ultraviolet catastrophe. Planck's proposal of quantized energy levels provided the necessary solution, suggesting that energy could only be emitted or absorbed in discrete packets, which he called quanta. Planck's work, although initially a mathematical solution to a specific problem, marked the dawn of a new era in physics. His quantization of energy was the first step in what would later become the quantum revolution, a framework that challenged classical ideas and brought forth a new way of thinking about the micro-world. Planck's constant, a fundamental quantity in quantum theory, became a cornerstone for subsequent developments in quantum mechanics, influencing key figures like Albert Einstein and Niels Bohr. Albert Einstein, in 1905, built upon Planck's ideas and expanded them with his work on the photoelectric effect. Einstein proposed that light could be described not only as a wave, as suggested by early theories, but also as a particle, a concept that was initially difficult to accept. Through his experiments, Einstein showed that when light shines on a metal surface it can release electrons, but only if the light has a frequency above a certain threshold. The wave theory couldn't explain this behavior, but Einstein's particle-like approach to light provided the answer. He proposed that light is composed of discrete particles, later known as photons, each carrying a specific amount of energy proportional to the frequency of light. Einstein's concept of photons was revolutionary. It gave light, both wave-like and particle-like properties, a duality that had never been considered before. This wave-particle duality of light would become one of the central features of quantum mechanics, which not only altered our understanding of light, but also of matter. Quantum mechanics suggested that particles could exist in multiple states at once, a strange and counterintuitive concept that became essential in explaining the behavior of subatomic particles. In the 1920s, Niels Bohr extended the ideas of quantization to the atom. His model of the hydrogen atom introduced the concept that electrons could only occupy certain discrete orbits around the nucleus. Bohr's theory was based on Planck's quantization, as well as Einstein's and others' ideas about energy exchange. According to Bohr, an electron could only exist in specific energy levels, and when it moved between these levels, it would emit or absorb energy in the form of light. This concept of quantized states within the atom was groundbreaking, and it led to a deeper understanding of atomic structure and the behavior of matter at the microscopic scale. The introduction of quantum mechanics radically altered the way scientists thought about the universe. It introduced a probabilistic view of reality, where certainty was replaced with uncertainty. This view was formalized in Werner Heisenberg's uncertainty principle, which stated that one cannot simultaneously know the exact position and momentum of a particle. This principle showed that at a quantum level, particles do not have definite states in the way classical physics had imagined. Instead, they exist in a cloud of probabilities, where their exact state is only determined when measured. In the 1920s and 1930s, quantum mechanics expanded to include the study of wave functions, superposition, and quantum entanglement, concepts that were essential for understanding the behavior of light and matter on the smallest scales. The development of quantum theory was also influenced by the work of other prominent scientists, such as Erwin Schrödinger, who developed the famous wave equation, and Paul Dirac, whose work incorporated relativity with quantum mechanics. Quantum mechanics not only resolved issues related to the nature of light, but also laid the foundation for modern technologies. Today, quantum mechanics underpins many technological innovations, such as semiconductors, lasers, and quantum computers. The work of Planck, Einstein, Bohr, Heisenberg, and others opened a new frontier in science, one where the classical laws of physics no longer apply and the strange behavior of particles at the quantum level reigns. In conclusion, the evolution of light's understanding reached a critical point with the advent of quantum mechanics, which completely transformed how scientists viewed the micro-world. The concepts of energy quantization, wave-particle duality, and uncertainty challenged classical ideas and led to the development of a new framework for physics. Quantum mechanics not only solved long-standing puzzles about light but also provided the foundation for modern technologies that have changed the world. The contributions of Planck, Einstein, Bohr, and others marked the beginning of an era of scientific discovery that continues to shape our understanding of the universe. The history of light, as understood by humanity, reflects a journey of curiosity, experimentation, and scientific breakthroughs. In the sixth keynote, the evolution of light theory stretches from the early classical understanding to the dawn of quantum mechanics. This story unfolds over centuries, from the first philosophical speculation to the revolutionary ideas that redefined the very fabric of reality itself. The initial exploration of light can be traced back to ancient civilization. In ancient Greece, the nature of light was a subject of philosophical and mystical speculation. Early thinkers, such as Pythagoras, believed that light was emitted from the eyes, and that vision resulted from the interaction of this emanating light with objects. His notion of light as an emanation gradually influenced later ideas about vision, though it was not until the work of Euclid and others that mathematical and geometrical frameworks began to form the basis for understanding the behavior of light. Euclid's work on the angles of reflection in the 3rd century BCE marked one of the earliest recorded studies on optics, presenting the idea that light travels in straight lines. This was a simple but important observation, helping to shape future concepts of light and reflection. In the centuries following the Greeks, the study of light largely stagnated in Europe. However, in the Islamic Golden Age, scholars made significant advances. One of the most prominent figures was Ibn al-Haytham, also known as Alhazen, who is often referred to as the father of optics. His experiments with light and vision provided the first clear understanding of how light enters the eye and how vision is a passive process of receiving light. Alhazen's work, particularly his Book of Optics, demonstrated how light behaves when it interacts with different surfaces. He rejected the idea of vision as an emission of light from the eye, instead concluding that light enters the eye and creates an image. His empirical approach laid the groundwork for future investigations into the nature of light and its role in human perception. It wasn't until the 17th century that light was systematically studied as a physical phenomenon. This period was marked by two opposing schools of thought: the corpuscular theory of light, championed by Isaac Newton, and the wave theory, which would later be promoted by Christian Huygens. Newton's corpuscular theory, proposed in the late 1600s, held that light was composed of particles, or corpuscles, which traveled in straight lines. This theory was based on Newton's experiments with prisms, through which he demonstrated that white light could be split into its constituent colors. According to his theory, each color was a result of the different size corpuscles, with colors differing based on the size of the particles. Newton's work on the nature of light was instrumental in shaping the scientific understanding of the time. His ideas on light provided a solid framework that helped explain reflection and refraction, and his authority in the scientific community made this theory widely accepted for nearly 2 centuries. Meanwhile, another scientist, Christian Huygens, proposed an alternative theory of light. Huygens suggested that light was a wave rather than a particle. This idea was largely based on his observation that light could bend around corners, a property that waves exhibit. In 1678, he published his wave theory, stating that light was a disturbance in a medium, which he termed the ether. According to Huygens, light traveled as a series of waves, and each wavefront of light acted as a source of new waves. This theory provided an explanation for the behavior of light that Newton's corpuscular theory could not account for, such as the phenomenon of diffraction. However, because the idea of ether as a medium was never proven, and the particle theory dominated for a long time, Huygens' wave theory did not gain widespread acceptance in his time. It wasn't until the 19th century that the wave theory gained prominence, again, due to the work of Thomas Young and Augustin Jean Fresnel. In 1801, Young performed his famous double-slit experiment, which provided strong evidence in favor of Huygens wave theory. Young observed that when light passed through two closely spaced slits, it created an interference pattern, a series of alternating bright and dark bands. This could only be explained by light behaving as a wave, as waves can interfere with each other in a manner that produces such patterns. The interference pattern observed by Young was a major turning point in the study of light, as it provided clear evidence that light exhibited wave-like properties. However, despite this evidence, many scientists still adhered to the particle theory of light, and the debate between the two theories continued for many years. In the early 19th century, Augustin Jean Fresnel further developed the wave theory of light. Fresnel's work on diffraction and polarization helped to cement the idea that light was a wave. He demonstrated mathematically that light could bend around obstacles and pass through narrow slits, producing patterns that could be predicted using wave equations. His work on polarization also showed that light was a transverse wave, oscillating perpendicular to the direction of travel. These developments were critical in further validating the wave theory and gaining acceptance in the scientific community. Maxwell's equations, formulated in the 1860s, marked the next major breakthrough in understanding light. James Clerk Maxwell unified the theories of electricity, magnetism, and light into one comprehensive framework, showing that light was an electromagnetic wave. Maxwell's equations described how electric and magnetic fields interact to form electromagnetic waves, and that light was one such wave. This unification of electricity, magnetism, and light into a single theory was a monumental achievement. Maxwell's work demonstrated that light did not need a medium like ether to propagate. It could travel through a vacuum as an electromagnetic wave, which was a radical shift in the way scientists thought about light. Maxwell's equations predicted that light, as an electromagnetic wave, travels at a constant speed, a concept that would later be confirmed by experimental data. Despite the success of Maxwell's theory, some mysteries about the behavior of light remained unresolved, particularly in the realm of high-frequency radiation, which led to the ultraviolet catastrophe. Classical theories, including Maxwell's equations, predicted that a black body would radiate infinite energy at high frequencies, but experiments showed a different result. The solution to this problem came in 1900 when Max Planck introduced the concept of energy quantization. Planck proposed that energy could be emitted or absorbed in discrete units, or quanta, rather than continuously. This idea laid the foundation for quantum theory, which would ultimately redefine the nature of light and matter. Planck's work solved the ultraviolet catastrophe and set the stage for a revolutionary new understanding of light. The early 20th century also saw the contributions of Albert Einstein, who extended Planck's ideas. In 1905, Einstein published his work on the photoelectric effect, demonstrating that light could behave as a particle, a concept that would become known as the photon. Einstein's work on light as a particle marked the beginning of the quantum revolution, showing that light has both wave-like and particle-like properties. This duality of light would become one of the central tenets of quantum mechanics, forever altering our understanding of the universe. The work of Planck, Einstein, and others in the early 20th century culminated in the development of quantum mechanics, a theory that radically changed our understanding of light, matter, and the fundamental nature of reality. Quantum mechanics, with its concepts of wave-particle duality, uncertainty, and energy quantization, provided a new framework for understanding the behavior of particles and waves at the atomic and subatomic level. In conclusion, the understanding of light evolved through centuries of exploration, from the philosophical, mystical ideas of the ancient Greeks to the scientific breakthroughs of the 19th and 20th centuries. The wave theory of light, developed by figures like Huygens, Young, and Fresnel, gained acceptance and led to a more accurate understanding of light's behavior. Maxwell's unification of electricity, magnetism, and light into a single theory provided a solid foundation for the study of light, and Planck and Einstein's work introduced the revolutionary concept of quantum mechanics. Together, these developments transformed the way we understand the nature of light and the universe. The journey of understanding light is a story filled with profound discovery, technological advancements, and paradigm-shifting theories. The seventh keynote explores the contributions of women and students in the movement for a separate homeland for Muslims in British India. The involvement of these groups was crucial as their efforts helped bring the struggle for independence into the public eye, demanding that the rights and cultural identities of Muslims be respected. In the 19th and early 20th centuries, these individuals played vital roles in mobilizing support for the creation of Pakistan. Women and students, though often overshadowed by their male counterparts in history books, provided critical momentum for the political and social movements that led to the establishment of a separate Muslim homeland. The contribution of women in the freedom movement of British India, particularly in the context of the creation of Pakistan, is often understated but was undoubtedly significant. Despite the limitations placed on women at the time, many Muslim women took part in protest rallies and social activities that advocated for a separate homeland for Muslims. Women like Fatima Jinnah, the sister of Muhammad Ali Jinnah, and Begum Hazrat Mahal, the wife of the deposed ruler of Awadh, played major roles. Fatima Jinnah, known for her strong leadership and determination, was a key figure in the All India Muslim League and supported her brother's efforts to secure a separate state for Muslims. She was not only a political figure but also worked tirelessly to rally support for the cause of Muslims in British India, particularly in the face of political resistance from the majority Hindu population. Begum Hazrat Mahal, on the other hand, became a symbol of resistance during the 1857 uprising when she fought against British rule after the annexation of Awadh. Her leadership and resistance demonstrated that women were not just passive observers in the political and social upheavals of the time but active participants in shaping the course of history. She mobilized people, provided refuge to rebel leaders, and defied the British Empire's forces with remarkable courage. Her role in the uprising was not just about resistance. It was a powerful statement that Muslim women could and would contribute to the cause of independence. These women, along with others, broke societal norms, not only by participating in the struggle for independence but by challenging gender norms and making their voices heard in a time when women were expected to remain in the background. Another significant contribution came from the students of the Indian subcontinent who played a critical role in the independence movement, particularly in advocating for a separate Muslim state. The All India Muslim League, which became the principal political party advocating for Pakistan's creation, had the active participation of students who became the voice of young Muslims across the subcontinent. Students were among the first to realize the importance of a political platform that would allow Muslims to secure their rights and cultural identity. The student movements in universities, like Aligarh Muslim University, which was the intellectual center of Muslim thought, provided the leadership and ideological support necessary for the Muslim League to gain traction in the fight for Pakistan. One of the most powerful symbols of the students' contributions to the movement was their involvement in the Lahore Resolution of 1940. Students from various Muslim-majority regions of India gathered and showed their support for the demand for a separate homeland. They understood that the future of Muslims in India lay in their ability to assert their political, cultural, and religious rights, and they became active participants in ensuring that these rights would be protected. The students' unwavering support for the Muslim League helped turn the Lahore Resolution into a powerful political manifesto that eventually led to the creation of Pakistan. The students also played a pivotal role in spreading the message of Muslim nationalism. They were involved in grassroots movements, campaigning for the protection of Muslim rights, and working to raise awareness about the political demands of the Muslim community. They circulated pamphlets, participated in debates, and led peaceful protests that demanded a Muslim state. Their involvement was not limited to urban areas but spread across rural parts of India, where they educated people about the importance of a separate Muslim identity. The students helped bridge the gap between the political leadership of the Muslim League and the masses, ensuring that the demand for Pakistan was not just a political elite movement, but a grassroots effort that involved every level of society. As the political atmosphere in British India became more charged and intense, the role of women and students became even more pronounced. The increasing visibility of these groups was instrumental in bringing national attention to the Muslim League's goals. Women and students, in collaboration with male leaders, helped orchestrate significant events such as the Quit India movement, and actively participated in protests that demanded independence. Their combined efforts amplified the calls for a separate Muslim state and put pressure on the British colonial government to address Muslim concerns. The participation of women and students was not limited to political activism. It extended into the social and cultural spheres as well. For instance, the All Pakistan Women's Association, founded by Fatima Jinnah, worked to address issues such as women's rights, education, and social welfare. It was through these organizations that Muslim women not only asserted their political voice but also demanded improvements in their social status, health, and education. The association provided women with the tools to engage in social reform, ensuring that the post-independent Pakistan would be a place where women could participate equally in the societal development of the country. The role of students was not only political and social but also intellectual. The early intellectuals and political theorists, many of whom were students, shaped the ideological framework of Pakistan. They established the theoretical underpinnings of Muslim nationalism in India, drawing upon the two-nation theory, which asserted that Hindus and Muslims were two separate nations with distinct cultures, religion, and ways of life. These ideas were crucial in articulating the demand for Pakistan, as they emphasized the need for a separate Muslim state to preserve the distinct identity of Muslims. The theoretical work done by students and scholars during this period helped frame the narrative of the Pakistan movement and garnered support from Muslims across India. As the demand for Pakistan grew stronger in the 1940s, it was clear that women and students had played a fundamental role in its creation. Their contributions were integral to the mobilization of support for the Muslim League's goals, and their voices helped to shape the political discourse of the time. Women like Fatima Jinnah and students from universities like Aligarh became symbols of courage, determination, and leadership, showing that the struggle for a separate homeland for Muslims was not limited to male political leaders but was a collective effort by all sections of society. In conclusion, the contributions of women and students to the Pakistan movement were pivotal. Their active participation in the political, social, and intellectual aspects of the struggle demonstrated that independence was not just a goal for the political elite, but for the entire Muslim population of India. Through their actions, these groups helped bring the message of Muslim nationalism to every corner of the Indian subcontinent, ensuring that the demand for Pakistan was both widely understood and strongly supported. Their role in the creation of Pakistan remains a testament to the power of grassroots movement and the ability of marginalized groups to influence national and historical change.